Welcome everyone, and thank you for joining us for the final installment of our Fall 2021 CSAFE Webinar series sponsored by NIST. Today we have Using Mixture Models to Examine Group Differences, an illustration involving the perceived strength of forensic science evidence. Our speaker today is Naomi Kaplan-Damari, who joins us from the Criminology Institute at the Hebrew University of Jerusalem. She recently started there after finishing her postdoc work, including this research, at the University of California, Irvine. Naomi, I'll hand it over to you.
So I'm very happy to be here, this time from the other end of the world. And the work I'm going to present today has to do with the way people understand forensic evidence. We are trying to evaluate population differences in the perception of forensic reports. And this is joint work with Professor William Thompson, Dr. Rebecca Hofstein-Grady, and my advisor in my postdoc research, Professor Hal Stern. So let's imagine for a minute that we are members of the jury and we see this evidence. And we are told that a fingerprint expert compared the crime scene print with the fingerprint of a suspect, and he found them indistinguishable. And the strength of this evidence depends on the quality and the number of distinguishing features in the print. And now the expert needs to explain the strengths of the evidence. So when reporting the evidence to the court, there are a few options of statements that an examiner might use. It can be the suspect was the source, or the observed evidence is 10 million times more likely if the suspect rather than a random person is the source, or it is highly probable that a suspect was the source. And there are many other options of statement that might be used, and we will present some of them later. But when we're just looking at these three examples, we can think which statement looks strongest to us, or which one is best understood by the jurors. And this issue of how to present evidence and how the different statements are perceived, and are they perceived in the manner that the forensic scientist has intended, has become an important issue in forensics. So before I introduce our study, I would like to introduce you to a study of Thompson et al. From 2018, who examined how lay people perceive the strengths of examiner conclusion statements. And their goal was to compare the different statements and determine their ranking, so to see which statement is perceived stronger relative to other statements. We will review this study more formally later, but what's important to note now is that the underlying assumption of Thompson et al. Was that all people are governed by the same preference, meaning there is a single homogeneous population. So in the past, forensic evidence was considered as very important ruling, even when they were not scientifically based. And there's a growing need both by the academic community and the courts to have a more scientific basis. And this need is expressed both in the National Academy of Science report from 2009 and the PCAST report from 2016. And these reports question the scientific foundations of many forensic disciplines, and they express the need for more modern statistics to establish these foundations. These reports have led to new research on the scientifically rigorous analysis of forensic evidence. And now let's suppose that as a result of these reports, we build up the scientific foundations and we have reliable and quantitative conclusions about the strengths of the evidence. Now the question turns to be, how would the court perceive the evidence? Do jurors really understand statistical testimony? What value do they give qualitative versus quantitative statements about the weight of the evidence? In other words, do lay people understand or statistical and non-statistical characterization of the evidence, and is it in the manner that the forensic examiner intended? So forensic scientists often compare items of evidence to assess whether they originated from a common source. This is true in many disciplines: DNA, fingerprints, glass, shoe prints, hair analysis, handwriting, and others. And if we denote by E the evidence, we have two propositions: the same source proposition, meaning that the sample from the crime scene and the sample from the suspect originated from the same source, and the different source proposition, that the samples have different source. And the logic that forensic examiners follow is that they examine these two samples, they identify similarities and differences, and then they assess how likely these similarities and differences are under the same source hypothesis and how likely they are under the different source hypothesis. And after they do that, they have to present the evidence to the court, and there are different approaches to the presentation of the evidence. The first is what's called the forensic conclusion as expert opinion. The second is a two-stage procedure. The third is the likelihoods ratio, and related to that, there is also the posterior odds. And I will now go over these different approaches. So the first approach, the forensic conclusion as expert opinion, is very common in many pattern disciplines. And basically, the expert analyzes the evidence based on his experience, training, and accepted methods in the field. And then he gives his assessment of the evidence that reflects his opinion. Typically, this opinion is reported as categorical conclusion, such as identification, inconclusion, exclusion, or some support, strong support, very strong support, etc. The second approach is called the two-stage procedure, where the first stage is called similarity, and this is basically a binary decision. Often statistical procedures are used to make the determination, and the examiner actually has to determine if the sample from the crime scene and the sample from the suspect agree on the characteristics of interest, and then he needs to say if these two samples looks like they're indistinguishable and can't be distinguished, a match. In the second stage, which is called the identification stage, he has to assess what's the probability of a coincidental match. The probability that two samples from different sources would be found as a match. The third approach is the likelihood ratio approach. We know that the goal of the trier of fact in the courtroom is to decide about the relative likelihoods of these two hypotheses that we introduced, the same source versus different source. And again, if we denote by E the evidence, S same source and S bar different source, then the likelihood ratio is the relative likelihood of the evidence under these two hypotheses. More specifically, the numerator assumes that they came from a common source and ask what's the probability of the evidence, and the denominator assumes there's no common origin and asks what's the probability of the evidence. And the denominator is analog to finding coincidental probability. So if, let's say that we calculate the likelihood ratio and it was found to be 6, then what the likelihood ratio statement means is that the evidence is 6 times more likely if the objects have the same source than if the objects have different source. But it's important to note that the likelihood ratio does not make any direct statement about the probability of the hypothesis. We're only talking about the evidence given the different propositions. If we do want to talk about the probability of the hypothesis, then we're actually talking about posterior probabilities. And we could do that by using Bayes' rule. Bayes' rule is a way to reverse the direction of the conditional probabilities and go from talking about the likelihood of the evidence given the hypothesis to talk about the likelihood of the hypothesis given the evidence. So this is the likelihoods ratio. And if you want to talk about posterior probabilities, we actually want to talk about this. This is the posterior odds. So this is actually Bayes' theorem written in terms of the odds in favor of the same source hypothesis. Again, this is the posterior odds, this is the likelihoods ratio, and this is the prior odds. So in order to go from talking about the likelihoods ratio to the posterior odds, there is this prior odds that we need to know. So a lot of people report not a lot of people, some people report posterior probabilities, and I think a lot of people think this is problematic. And the reason that this is problematic is that in order to calculate again, these posterior odds have to say something about the prior odds. So the forensic examiner is often what you need to do is to have a subjective assessment of this prior odds. And this is not really part of his scientific domain. It's more of the role of the trier of fact, not the examiner. I think I confused. So this is not the role of the examiner. It's more the role of the trier of fact. And this is why reporting posterior odds is considered problematic. Okay. So these different approaches that I just talked about translate to different type of statements that are used in court. So the expert assessment based on the experience and training, et cetera, is typically summarized by categorical conclusions. For example, here, the suspect was the source, or I individualize as coming from the finger. The two-stage procedure is summarized by random match probabilities. For example, here, 1 person in 10 million is expected to provide this degree of similarity. The likelihoods ratio is summarized by likelihoods ratio, and also by what's called the strengths of support statements, which is actually, oh, I can't use the buttons anymore, I think, because the buttons of the Zoom is on them, so I'll figure it out. But so the strengths of support is also, it's a verbal likelihoods ratio. And this, what we see here is like 10 million times more likely if the suspect rather than a random person is a source. So this is just an example of regular likelihoods ratio. And the verbal likelihoods ratio is an example is extremely strong support for same source theory or very strong support, etc. Okay. And related to the likelihoods ratios, as we said, is the posterior odds, and this is often reported as source probability statements. An example for that is a practical certainty that the suspect was the source, highly probable, moderate probable, and etc. Okay, good. So going back to the Thompson study, they examined how lay people perceive the strengths of these statements. They wanted to compare the different statements to determine the ranking and see which statement is perceived as stronger than other statements. And for that, they conducted 3 separate online studies with jury eligible US from Amazon Mechanical Turk, which is an online labor survey often used in social sciences. And they had 3 studies. The first 2 studies had to do with fingerprint comparisons, and the third was a DNA comparison. And the number of participants were 120 for the first, 121 for the second, and 138 for the third. Okay, so for example, in the first study, participants were asked to imagine that a fingerprint expert compared the crime scene print with the fingerprint of a suspect and found them indistinguishable. They were then told that the strength of the evidence, just like I told you at the beginning, depends on the quality and the number of distinguishing features in the print. They were told that the expert needs now to explain how strong the evidence is in a particular case. And now they were asked to evaluate a series of statements that the expert might make about the strength of the fingerprint evidence. So the original attempt was to have people rank many statements, but it turns out that it's really hard for people to reliably rank multiple statements, and they provide more meaningful responses when they're asked to evaluate the relative strength of only 2 statements or statements in pairs. And here is an example of what was used in the study. So which of the following 2 conclusions would seem stronger if you heard it, meaning more convincing to you that the suspect is the source of the print? One is I individualized the crime scene fingerprint that's coming from the finger of the suspect. And the second, it is highly probable that the suspect is the person who made the crime scene fingerprint. So, excuse me, the first is an example of a categorical conclusion, while the second is an example of source probability. So there were 9 statements which were compared, and that created a pool of 96 possible paired comparisons. But each participant only evaluated 16 pairs that were selected randomly. Some statements were used in all the studies, and others were only in some. For example, the random match probability was used in studies 2 and 3, random match probability 4, RMP3 was used in all 3 studies, etc. Okay, so I know we have a diverse audience, so I'm going to go light on the notations and formulas and more on concepts. But let's denote why Kij equals 1 if statement I is preferred to J by subject K and 0 otherwise. We know by big K the number of objects, M is the number of statements, and lambda I is the notional of strength of the statements. So this expresses how strong the statement is perceived. And if we know these strengths of the statements, we can know the probability that statement I is preferred to J by a specific individual. So pi ij here is the probability the statement I is preferred to statement J. And this is known as the paired comparison model. And we can see that it does depend on the difference of the strength parameters, the lambdas of the 2 statements I and J. And F here is a cumulative distribution function, where if this distribution function is a normal CDF, this is called the Thurston-Mosteller model. And if it is a logistic CDF, it's called the Bradley-Terry model. And we will use the Bradley-Terry model, so the logistic CDF. And this is how it looks like. So this is the probability in our case that I is preferred to J. And what we see here, if the x-axis is the difference between lambda I and lambda J, let's assume for a minute that lambda I is much larger than lambda J, so we're around here. In this case, the probability that I is preferred to J is closer to 1, very high. If lambda I is very small compared to lambda J, so we will be in this area. In this case, the probability that I is preferred to J is very small, it approaches 0. If lambda I and lambda J are very relatively close, then this would be close to 0. And in that case, the probability that I is preferred to J is close to 0.5, like a flip of a coin. And that means that the individual doesn't have any preferences between these 2 statements. So the aim of the analysis, again, the Thompson analysis, was to make inference about these strength parameters, these lambdas, and so that we can understand their position, relative position of the statements. The likelihood of the Bradley-Terry model looks like that. Again, this is pi ij, the probability that I is preferred to J. This is the probability that J is preferred to I. And we go over all the statements that subject K compared, and we go over all of the participants in the study. And what we can see from this likelihood is that if we add a constant to all of the lambdas, since what's important here is only the difference between the lambdas, nothing will change. So if we add, for example, 6 to all the lambdas, we will be still with the same model. And for that reason, we need an identification constraint. We choose one of the lambdas as a reference statement, and that allows us for the model to be identifiable. Okay, so here are the results of the Thompson study. What we see here is a picture of the ranking of the statements. These are the values of the estimated strength parameters over the 3 studies. And what we can see here that, first of all, statements that the author viewed as strong were ranked significantly higher. For example, SOS4, which is extremely strong, was perceived stronger than SOS2, which is moderate, and that was perceived as stronger than SOS1, which is weak. So this is one thing that is kind of logical. And they also found that there was no category where all the statements were perceived as stronger or weaker than all statements in another category, meaning there's no case where all the RMPs were stronger than all of the CC, for example, categorical conclusion. They found that was surprising to them that CC3, which means identified, and CC4, which means individualized, that were believed to be stronger, the strongest statements, they were not perceived that way. And in fact, the match, which was marked as CC2, was found to be stronger than these two statements. And from that, they also concluded the match is dangerous. It was given similar weight as a random match probability 4, which means 1 in 10 million. They found that like-use ratios are powerful. They're strong as or stronger compared to the random match probabilities, 1 person in X. They found specifically that like-use ratio 4, which is 10 million times more likely, is perceived stronger than suspect was the source. 100,000 times more likely is perceived stronger than highly probable, and 100,000 times more likely is perceived similarly to extremely strong support. So this was the Thompson study, but the underlying assumption of this study was that all people are governed by the same preferences, which is a limitation of this study. Thompson also gathered information about each participant. This information was not used in their study. The information they gathered was the age, the self-rated numeracy, which is the perceived ability and preference to perform mathematical tasks, the gender was collected, educational level from high school to doctoral degree, and they also asked the question of how knowledgeable are you about forensic science when 1 is not knowledgeable and 7 is extremely knowledgeable. So our question is perhaps there are subsets of the population which actually interpret the statements in a different way. And we have this information that was gathered for us to investigate that. So what we want to do is we want to take this study one step further, and we do that by examining whether there are subpopulations which interpret statements differently, and whether these subpopulations can be characterized. And so there are 2 approaches in doing that. One is to look at different subsets of the populations, which can be defined by covariates, for example, male versus females, and then look at the separated strength parameters and see if they differ. A more general approach is to actually allow the data to determine if there are subpopulations. Okay, so the first approach is more an exploratory analysis. So we define a priori the specific characteristics. Here we have it from the data, and then we investigate the difference in the strength parameters. In the original study, what we did is we split into to 2 groups. So gender, we split to female and male, and then all the other variables, we split by the median values, and we had a group of low age, low SNS, high SNS, etc. And what we found is there appears to be differences based on the SNS. And when we look at the Bradley-Terry model that was fitted separately to the 2 SNS groups, we found it to be an improvement over the Bradley-Terry model that was fitted to the entire population, as Thompson and al. did, and we found it in all 3 studies. And when we look at the SNS, the results of the SNS analysis, what we see here is that this is the low SNS and high SNS, and these are the strength parameters for each of the 3 studies. So what we see is that the ordering of the statements in these high and low SNS groups are relatively the same, but the differences is more in how the high and low groups distinguish between the statements. Meaning, if we look at the range between the highest statements to the lowest statements in the low SNS group, it's between minus 4.65 to 0.79, meaning that the probability that the strongest statement is preferred to the weakest statement is around 0.99. But when we look at the low SNS group, the range is much smaller, and the probability that the strongest statement is preferred to the weakest statement is 0.93. So, but a limitation is in using this approach is that we can only do the analysis for each characteristic at a time. The approach that I'm going to present now does not require us to identify these characteristics in advance. And it uses mixture models to identify the subpopulation. So this mixture model allows us first for various subpopulation with possibility that each subpopulation has different ranking of the statements. And it also allows us for the possibility that covariates explain out the subpopulation membership. So we denote by xk the covariate vector of subject k, and by ik the statements that subject k compared. And before we move to the more general model, I would like to give you some intuition. So we're going to build a cluster model, and I'm going to use cluster subpopulation, which mean the same. So let's just imagine now that we only have 2 clusters. So each cluster has its own vector of strength parameters. Lambda 1 is the vector of strength parameters of cluster 1, and lambda 2 for cluster 2. And we do not define any clusters in advance. We just want to explore and see if they actually exist. So let UK define the cluster the person K belongs to. So in our case, since there are only 2 clusters, it can either belong to 1 or 2. And the model for cluster membership is logistic regression. And so the probability of belonging to the first cluster is this. And then the probability of belonging to the second cluster is 1 minus the probability of belonging to the first cluster. So this is the probability. And it is possible to simultaneously estimate the cluster membership and the parameter that describe the cluster. And we can do that by using the EM algorithm, which is an approach of estimating parameters when there are missing data. And in our case, the missing data are the cluster membership. So the EM, what it does, it has 2 steps. And if we know the strength parameters, the lambdas, we can estimate the cluster membership probabilities. And now after we estimated the cluster membership probabilities, we can update the lambdas. So this is how this algorithm works. And in more generally now, let's assume that we don't have 2 clusters. Now, the number of clusters can be big U, where again, UK is not observed. We don't know the cluster membership. The model for that cluster membership is this. And the likelihood is similar to what we saw before, where this is the probability that I is preferred to J in cluster UK. This is the probability that J is preferred to I. And this is the probability of belonging to cluster UK. And we go over all the statements that subject compared, go over all the possibilities of the clusters for that person, and we go over all of the individuals. And we inference by using the same EM algorithm that I presented to you. So now for the analysis, we start by assuming that we have 2 clusters. So these are the results of the first study. We see that the algorithm identified 2 populations, one that consists of 75% of the population, and the other 25% of the population. And what you see here again is the estimated strength parameters of the different statements. This is the standard errors. And what you see here is a visualization of the table here. So these are the values of the statements. It allows us to compare visually the 2 groups. And again, as in the Thompson analysis, a high estimate corresponds to a statement which was perceived as a strong statement. So what we see here, that group 2 really does not differentiate between the statements. It really looks like they don't really know what they're doing. The first group, the order of the statements was found to be the order by Thompson et al., the same order that Thompson et al. Found. A possible explanation that maybe the first group paid more attention to the details of what the expert was saying, or maybe they were just more capable of processing the significance of the statements the examiner presented. But this is an interesting picture. When we tried to characterize the first group, we found that these are people with high SNS, age, and education. And we can see that every increase in 1 point in the SNS increases the odds of belonging to group 1 by a factor of 2.6. Now, moving to the second study, we see that here the algorithm identified 2 groups, 1, 59% of the population, group 2, 41% of the population. Again, these are the estimates. And when we look at this picture here, we see an interesting picture. It looks like the 2 groups agree on the random match probabilities, but group 1 finds the categorical statements as stronger than the quantitative random match probability statements, while group 2 favors the quantitative statements. So for example, the probability for group 1 that CC4 is preferred to random match probability 4 that individualizes is preferred to 1 in 10 million is 0.62, while group 2, this probability is 0.03. And what's interesting in this study is that we found that there was no covariate that really helped us distinguish between these 2 groups. Okay, when we look at the third study, it's nice because it resembles the second study. We see again that these 2 groups, they agree on the random match probability, but again, they interpret the categorical conclusion statements relatively different. Group 1 finds CC5, suspect was the source, as the strongest statement as opposed to what you see here in group 2. And also we see that group 2 doesn't really differentiate between the likelihoods ratio and random match probabilities, but group 1 slightly prefers the likelihoods ratio. So the key finding is that essentially we see that in every subpopulation there are consistent ranking within a category, but the spaces between the items might vary. For example, in some cases they're almost equal, but in other cases there are large gaps. We found that there are differences in the relative standing of categorical and quantitative opinions. We saw it especially in studies 2 and 3. And these really suggest that there are different kinds of people. So now we move to the question, in a real data set, how can we really decide if the 2 cluster model fits better than a 1 cluster model? So one kind of basic thing to do is to look at the likelihoods of a 1 cluster model and look at the likelihood of a 2 cluster model, look at the difference and compare it to a chi-square distribution here with a 9 degrees of freedom. The problem here is that this is a special case where the p-value here cannot be really calculated in the usual way, since the likelihood ratio test does not have the usual null distribution. I won't get into the details, but one approach for calculating the p-value is and address this issue is to conduct a Monte Carlo likelihood ratio test, which will help us determine the number of clusters. So I'll explain what we've done. The Monte Carlo likelihood ratio test was calculated in a way that what we did, we simulated data that came from a 1 cluster model. This was the true model. And then we fit a 2 cluster model and a 1 cluster model to this simulated data. We calculated the likelihood based on these 2 models. We compared them. We looked at the difference between the likelihood. And this gives us some idea of how big a change in the likelihood would be expected as a result of chance alone. we repeated this over and over again to get a distribution of the difference in the likelihood. And then we compared it to the real data. It's probably hard to understand it that way, so I have a picture that will help us understand. Again, we assumed we simulated data that we know that comes from a one cluster model. We then fitted one cluster model and two cluster models. We have the likelihood of the two. We calculate the differences between the likelihoods, which tells us the difference that is expected by chance. We do it over and over again, so we have this distribution of the differences that result in just by chance. And then we compare it to what we see in the real data. This is the difference between a two cluster model and a one cluster model. So from that, what we see is that there is evidence that the data did not originate from a one cluster model. Okay, so here are some conclusions. We see that there is evidence that different subpopulations do tend to perceive statements presented by an examiner differently. So even when solid scientific evidence is presented, it may be interpreted at least by a certain percentage of the population in a way that is different than what the examiner intended. And also, we saw that in studies 2 and 3, the groups seem to agree on the interpretation of the random match probabilities, but one subpopulation always prefers the categorical statements. And this finding may reflect that there is a general difference among individuals in their ability to make the use of quantitative information. So I think the final conclusion is that if the population of potential jurors does consist of subgroups that respond differently to expert testimony, then we have to explain our finding in multiple ways to assure that the testimony is really more broadly understood. The problem is that this can be confusing and challenging. So what I would like to do now is just spend a few more minutes and present some future work. So what we saw in the Thompson analysis was the classical paired comparison model. And when we use this model, the assumption is that given the strength parameter, these lambdas, the results of all comparisons are independent, whether within a single participant and across participants. And it's very possible that results of several paired comparisons that were made by the same individual will be in fact dependent, will not be independent. So again, this is the classic model. In this model, everyone has the same order of lambdas. What we showed today is a model that can be represented by this model is a model where we have different clusters. So UK indicates a cluster membership, which is not observed. U can be multiple clusters. But the problem with these models is that depending on the amount of data we have, this reflects the number of clusters that we can identify. What we're working on now is a model that has random effects. So here we look at the classic paired comparison model, but we added a random effect component, which is a factor for the individual. So if we look at a model that everyone has the same order of lambdas, but now the alpha allows for the strength of the opinions to vary. So the alpha here expresses the heterogeneity in the population and how extreme an individual is relative, or how extreme the preferences of an individual is relative to the population. We're also working on to see if in some cases maybe we want lambda and alpha to depend on the characteristic of an individual. And another option is to add this alpha factor to a model that has multiple clusters. So I guess this is it. Thank you very much. And I'm going to look now at the Q&A. Okay. Okay, so the first question is twins close relatives. Can you elaborate what you meant? Or there's a, okay. Should we consider the possibility that people on a jury may interact and influence each other? That's a very interesting question. I think here, so in this study, obviously they were independent. You know, each participant ranked it independently than others. It's, of course, when we go to the actual determination, juries can influence one another. I think what we're investigating is even before that, the kind of the fact that different people perceive statements differently. It's true that there can be all other influences later, but I think we're one stage before that. Thank you for that question. Do culture affect perception? Interesting. If we had these variables, it would be very interesting to investigate. But we have no idea about it. One thing that is, I think, very interesting and nice, but also frustrating in a way, is that what I showed you here, the second approach. So what we have these clusters that were identified by the algorithm. So it's very nice. It's very interesting that we see these really big differences between these groups, but we don't know how to characterize these groups. Only in the first study we could say something about the SNS there, but sometimes we don't know because we didn't collect enough characteristics, I guess, that we can really identify these groups. But that will be something interesting to investigate if we had collected that data. Did I miss any questions, or?
I don't think so. Does anyone else have questions for Naomi? This is your chance. James, if you're still here and you're willing to elaborate, I know your twins close relatives comment was early on.
Right.
If you remember what the topic of discussion was at that point, that might be helpful. And
I'm trying to go to the beginning of the presentation just according to time to see if I can guess what the question was about. I was probably around here. Oh, I have no idea. Let's see, okay. For the expert witness, they present the effect. How should they present the effect of twins or close relatives under presentation of evidence? I'm not sure, I don't quite understand how it relates exactly to what I think we're more talking about how different statements are perceived. There are probably other issues of presentation, meaning here we, like, how do they respond to qualitative versus quantitative? Because these are the different statements that we compared. I don't have a lot to say about other issues with presentation of evidence. Obviously very interesting to think about, but it's not something that I can, I think, answer from what we've done. I'll move to another question. Any intervention to affect the individual jury to the perception? I don't think I understand exactly what you meant. You think you can help me understand the questions?
I think my interpretation is they're wondering if there's any way that early intervention can impact those jury perceptions.
Okay, thank you. So one thing that I don't know if it's even feasible, but let's say that we know that there are these different populations. One that that understands it, better, I guess, by using quantitative statements, and the other more with a categorical type of statements. And let's say that we found that this has to do with their SNS, the numerical ability. Just all these are assumptions, but if we do that, maybe even before a trial, begins, when you actually choose the jury, you can like it was done in the study, you can understand what their level of SNS, for example, is. And then according to that, you can try to figure out what's the best way to present the evidence in this jury that you have. So it's not really exactly relating to what you asked, but this is some way that maybe this research can be used. In terms of interventions, maybe you mean to try to understand what they understand and what we can do to improve their perception. That's very interesting. I don't have something on the top of my head because there's limitation. We can't really, during the trial. I'm not sure how we can, stop and see where they're at, what their perception is. But that's fascinating. Yeah. I'll have to think about it.
I'll give folks maybe just another couple seconds if they have questions or follow-up questions to put those in the Q&A feature.
Okay, so one question is, could an expert witness combine approaches to reach out to different groups? So that's, I think, what we were thinking. That was one of our recommendations. Although I have to say that the downside of that, it might be confusing if we don't know what's the effect of reporting in many different ways. But that's the line we were thinking, that in that way you can capture the most people, and they will understand it hopefully in the manner that you intended.
Naomi, thank you again for joining us today and for sharing this research with everybody.
Thank you very much.
To everyone else, thank you for joining us, and we hope you have a great day.